glucose. Ah, sugar, sugar, you help me make ATP.
Welcome back. In the last video we talked about why it's important to keep a constant internal environment, and how if we don't have a constant internal environment, such as our temperature being checked at 37 degrees Celsius, that we have problems in terms of our enzymes and other things. In this video we're going to cover the next point, which is quite related. And it's talking about, last video we talked about why it's important to keep a constant internal environment. In this video we're going to talk about how that's actually possible, how we keep a constant internal environment. So I read the actual dot point. It says, describe homeostasis as a process by which organisms maintain a relatively stable internal environment. So we're going to talk about how it's possible to maintain a stable internal environment, or relatively stable internal environment. And that's through homeostasis. So I'm going to describe what homeostasis is. And the actual verb is describe, so we have to describe it. Now, before I start, I'll give a quick analogy. What you have here is you have a person driving a car. There's a speedometer down here, and he's told to maintain a roughly 60 kilometers per hour. But when anyone's driving, anyone's driven before, it's hard to maintain that exact value of 60 kilometers per hour. So if a person's wanting to maintain at 60 kilometers per hour, what's going to happen is it's going to be, sometimes it's going to be at 50, let's say 57 kilometers per hour. Sometimes it's going to be at 65 kilometers per hour. Sometimes it might be a bit too low, sometimes it might be a bit too high. And the way he can keep it at exactly 60 is by using the brake and the gas pedal. So what you can imagine, the relatively stable internal environment. The relatively stable internal environment is saying, okay, we want to keep it around about 60. And the way we do that is through homeostasis. And what homeostasis is detection and response. So first we have to be able to detect a change. So you can imagine our eyes do that. Our eyes help us detect change. So here he's quite happy, we're at 60 kilometers per hour. And all of a sudden, if we go too high or too low, he becomes shocked. The eyes see that change and send that signal to our brain, where it gets interpreted. Right? So if we then go too high or too low, that the eyes will detect that change, and they will send a signal to our brain, and our brain tells us to either brake or press on the gas if we've gone too high or too low. So the gas pedal and the brake pedal are our response. So what happens if we're at 57? Then we're going to go press on the brake, which is our response. That's not the brake, the pedal, gas pedal, gas. So press on the gas and get back to about 60 kilometers per hour. And if we are at 65, we want to go back to 60, what do? We press on the brake this time, not the gas. And then get back to about 60 as well. So these are ways that we can keep a relatively constant internal environment. We have two mechanisms to help us. Now I won't talk about them that much detail in this one. I'll talk about more in the next video. But it's detect and response. And you can imagine detect to be our eyes, always observing any change that might occur. And response being what happens if we see that change. And the speedometer is kind of the analogy for homeostasis. We want to keep it at a certain speed limit, but we won't be able to do that at all times because it's almost impossible. But if it goes too high, slow, we have ways to bring it back up. So what is homeostasis? Describe homeostasis. The word homeostasis actually means similar. So homeo means similar, and stasis means keeping still. So you can imagine homeostasis to be a way that we can keep our constant internal environment very, very stable, very, very similar. And the word itself already suggests that. Now, if you had homo means same, right? So homeostasis would be keeping it the same, whereas homeostasis is keeping similar. We don't have it exactly the same. It's not always going to be 60 kilometers per hour exactly. Even if we try to control it, we'll still won't get to 60 kilometers every time. We keep it very similar, not exactly the same, but very similar. And that's what homeostasis is. So it's not homostasis. Homostasis would be keeping the same. It's homeostasis, which means keeping very similar. Now, the ways you can look at it, I'm going to talk about detection and response quickly about all of these examples, is we've got temperature, for example. we want to keep our temperature at that set point. And that set point is just the ideal point that we want to have it at. That's usually about 37 degrees Celsius for humans. Different for other animals, but for us it's 37 degrees Celsius. Now if it goes too low or too high, first what's going to happen is we're going to have to detect that change. Detect. In this case, I'm going to talk about more in the next video. It happens at the receptors. So receptors are kind of our eyes in our body. They do the same thing. They detect the change. So if it's at that set point, that's here, these parts are perfect. That's where we want to keep it at. But often what happens is we'll just go either too low or too high from that point. So for example, if we go too high, so if a body temperature goes too high, a response will happen. So that receptor has detected a change, and then the response happens. And the response could be, for example, if it's too high, could be sweating. And sweating will help us bring it back down to 37 degrees Celsius. There are more different types of responses that help us do this, but this is one example. If it's too high, the response will be sweating, which will bring us back down to 37 degrees Celsius. If it's too low, so for example, if it's right about here, and our body first detects it through these receptors, and then brings it back up, and it can do this for one of the responses that you can do this with is shivering. So shivering, for example, if we shiver, our body heat increases, so we might go from 36 back to 37. That's just two examples of how we can maintain that constant internal environment in terms of temperature. So there's a way that we detect the change, which is through receptors, and then we've got sweating when it's too high and shivering when it's too low to help us bring it back to 37 degrees Celsius. Now pH, so for example, if we have a pH of 7, that's ideal for humans in most of our body, except for our stomach. Neutral pH of around about 7 is good. So that's our set point. A set point is what we want to keep it at around about that. Again, the detection part, so how do we detect change? Detect happens through these receptors as well, like I did with the previous example. And I go over receptors more in detail in the next video. But if it's too acidic, so if the pH is too low, what happens is the response, if it's too acidic, too low pH, would be to actually breathe more. We actually breathe out carbon dioxide, and breathing out carbon dioxide decreases our acidity. So if we have too low pH, our response would be to breathe more, which brings it back up. And if our pH is too high, so on the other side, if our pH is, let's say, 8, the response will be actually to breathe less. And that keeps our CO2 inside our body and brings our pH down. Right, so again, we have a way that we want to have a set point, which is about 7. If it's too high or too low, that will be a detection part, receptors that detect that change. And then there'll be a response, or for both, if it's low or too high, to bring it back down to normal levels. Now, water levels, also want to keep those water levels at a constant level. And if it goes too high, first of all, again, there's a detection part. So detection is, like in the previous examples, is a receptor. So the receptors are eyes that detect that change. And once that change from the normal state has been detected, there's going to be two things happening. Either it's going to bring it back down or bring it back up. So for example, if we have too much water in our cells, we're going to have a constant dilute urine. So that means we produce dilute urine, which means we produce lots of urine if we have too much water. And that's a response for if we have too much dilute urine. And if we produce too little, or if we have too little water in our system, we produce concentrated urine. So the kidneys do this. Concentrated urine means we don't produce much. So a response for too little water. And that makes sense. We have the detection part, and then we have responses to bring it back down if it's too high and bring it back up if it's too low, to help us keep a constant internal environment in terms of water as well. So sugar. Sugar, we obviously want to keep a constant blood glucose. So this is about blood sugar levels. And we have two hormones that do this. So again, we have the detection part, which is our receptors. And then we have insulin and glucagon. These are two different hormones. glucogen. If our blood glucose is too low, then we will produce glucogen. So glucogen increases blood glucose. And insulin is the opposite. If it's too high, we produce insulin, and insulin lowers blood glucose. So we have two different mechanisms, two different responses to help it bring it to its normal set point. If it's too high, we produce insulin. If it's low, we produce glucogen. And what you might have seen some people do with type 1 diabetes, they will constantly monitor their blood glucose levels for this kind of device. And that's to check their device, because in their case, the often type 1 diabetes people don't have working insulin, they don't produce their own insulin, so they can't lower their own blood glucose levels. So they have to check it to see if it's what the levels are. If it's not good enough, if they have to inject their own insulin through an injection because their body doesn't produce it. So in this case, one of their responses doesn't work properly, and they have to do it through injections. But these are all different ways we can maintain responses, we can maintain our constant internal environment, and they're all important for different reasons. Now I'm going to quickly show you an animation as well, not a simulation, to show you how important it is to keep a constant internal environment. So what you're about to see is it's just different levels for blood delivery, oxygen needs, blood pressure, body temperature, and glucose levels. All of these things have been maintained in the constant internal environment. What happens if they're not? You'll see in a second. So I'm going to start the animation. So you can see here, this person, you have to keep it all in the greenish area. And if not, then she's going to feel really ill. So you can see it on the side. You have to try to keep it at it's actually quite hard. But homeostasis does that. So homeostasis keeps it at a constant internal environment. So I don't have to do this for my body. The body does it by itself. But you can see how she feels if it goes into red area. She feels quite ill. And I'll show you what happens if something goes bad. So I don't feel so good because it's not perfect. But if you make it really bad, she's feeling really ill. And eventually now you did not maintain homeostasis, she has actually died. So the body needs to keep doing this, because otherwise it's going to be a big problem in our body. And at that point it says describe homeostasis as a process by which organisms maintain a relatively stable internal environment. So homeostasis was all about keeping a similar level for different body processes, such as keeping temperature the same, pH the same, body water levels the same, and blood sugar levels the same. There were two different things we had to do to make that happen: detect, which is detecting the change, and response, which is responding to that change. So that's how homeostasis works. And then there are specific examples for responses for each different thing, such as if our temperature is too low, we shiver. If it's too high, we sweat. But it's all about keeping that constant internal environment. That's how homeostasis works. So hopefully that made sense.
Thank you for watching.